Good day to you. In another video, we explored the relationship between force and momentum in the formulation of Newton's laws of matter and motion. In this video, we'd like to do the same thing, but look at the relationship between energy and work. First, some historical things to keep in mind. Back in the 19th century, when the age of steam, it was pretty clear to people that engineers that there was a quantity called energy that could be used to do work. But it was uncertain what the actual relationship between energy and work was. And of course the desire on the parts of engineers was to formulate a definition of energy in the same kinds of terms that Newton formulated work. And this is a serious problem because Newton specifically referred to particles of matter with mass in motion, whereas engineers in the 19th century realized that energy could come in a variety of forms, the connection of which to matter and motion was sometimes a little bit obscure. So being able to understand the relationship between energy and work was an important problem that physicists of the 19th century had to solve. Let's start off exploring this with a little puzzle. Let's take, of course, Newton's definition of work, and work is force times the distance moved. You exert a force over a distance, moving an object over some distance, and you've done work on that object. If we take our units of that, the units of force are, of course, newtons, and the units of distance are, of course, meters. And from Newton's first law, we can break newtons down into its fundamental dimensions. A newton is a kilogram meter per second squared. And to get work, you multiply the units of newtons times the units of distance, which are meters, and you come out with a unit known that can be designated as kilograms meters squared times second times the minus seconds squared, or kilogram meters squared per second squared. This unit is known as the joule. Now, one of the things that engineers did was they came to understand the relationship between mass traveling at a certain velocity, and that was somehow related to energy. And let's take another example over here. Let's take a form of energy called kinetic energy. That is the energy that is in a body that is in motion. And the formula that lets us calculate the kinetic energy of a body in mass is equal to 1/2 times the mass times the velocity squared. And it's a fairly simple thing to break down the units here. Of course, the units of mass are kilograms, and velocity is meters per second. We square that, and we end up with units of kilograms meters squared per second squared. And of course, the units calculated from Newton's definition and the units calculated from matter in motion are identical. The units of kinetic energy are joules, just as the units of work as defined by Newton would be a joule. Dimensionally, they're identical. Now, the question is that coincidence, or is there some fundamental relationship that actually makes these two units come out the same? We suspect that it's not a coincidence, that in fact they are related somehow, but we can't prove it really until we've worked through the whole problem. So let's come back to our basic problem. Let's take a mass, and that's sitting there at point A, and we want to move that some distance to a point B. In order to do that, we have to exert a force on that, and we will move that object from point A to point B over a distance d. And of course, we come back to our formula. The work that is done during that process is equal to the product of the force times the distance. Now, we saw in our earlier video that the action of a force upon an object is to change its momentum. And so we derived a relationship that showed us that force was actually equivalent to a change of momentum. And so we can reformulate this equation right here to this form. We can say the force is a change of momentum, and of course remember we defined momentum with the symbol P, and the delta refers to a change of momentum, and we multiply that times the distance moved, which is d. We also discovered that a change of momentum is related to Newton's first law, so that the change of momentum is actually equal to an acceleration of a mass. So again, we can reformulate this equation right here. Work is equal to a mass, the product of a mass that is accelerated, which we will abbreviate as an A, moved over a distance. Now this is a fundamental relationship right here because it's derived basically just from Newton's first law and the equivalence of force with a change of momentum. We can carry on then and take this to its logical conclusion. Work is equal to a mass times a change of velocity over time times a distance. Change of velocity over time for distance. Let's carry on over here. The change of velocity over time has units of meters per second over seconds. So we can reformulate this equation. Work is equal to mass times a change of position, distance, over a change of time, and this is a change, the change of velocity is a change of distance over time, and then of course we have this multiplied out by the distance moved. So this equation right here, this relationship right here, is basically this relationship right here, okay? All right, now let's work out what the units are. Mass is kilograms. Delta x is meters. Distance is meters. Delta t is time. T is time. And multiplying those out, we get a system of units that is kilograms, meters times meters, meters squared, seconds times seconds in the denominator, seconds minus 2. And this is the same units, the joule. And so what we see here is deriving from some very simple principles of momentum and this relationship of momentum to force, we can demonstrate with a quite simple mathematical proof that there is an equivalence between work that is done by making a body move under the influence of a force and the kinetic energy of that particle or that mass as it's moving. So what we have here in a system like this is we have a mass with a particular momentum that implies that it's going to have a particular kind of kinetic energy, and the application of force is going to result in a change of the kinetic energy as that mass is accelerated. And the change of kinetic energy is the fundamentals of the ability of machines to do work. It also points us to some fundamentals about the relationship between kinetic energy, pressure, and other kinds of physical quantities. All right, well, that's all for now, and we will see you at another time.